Hi, my name is James. I am here with my teammates Jacob, Jenny, and Lucy to present our project AutoPPL, or Auto Probabilistic Programming Language. This project started out for an undergraduate course in C++ design at Columbia University. And in this talk, we would like to share what we learned about expression templates and concepts and how they help produce performant and type-safe code. So what is AutoPPL? So AutoPPL is a C++ template library for probabilistic programming. Now, historically, people wrote a custom language specifically designed for this application. But through expression templates and concepts, for the first time, we have a high-performing PPL that works natively in C++. And for our library, if the user specifies the C++20 standard, then it will choose the implementation using C++20 concepts. But we do support C++17 as well, but at the cost of weaker type constraints. So in this talk, we're first going to motivate probabilistic programming, what it's about, what it aims to solve. And afterwards, we'll look at a simple hello world example, and afterwards, a slightly more complicated example of medical diagnoses. And then afterwards, we'll talk about some benchmarks and performance against an existing probabilistic programming language called STAN. And afterwards, talk about some of the technical and implementation details and end with a demo.
All right, so first, probabilistic programming languages are motivated from the Bayesian worldview. The Bayesian worldview states that the world is probabilistic and that it is influenced by causal relationships. As you can see, causal relationships are represented in models like the one you see on the right. Using the Bayesian worldview, we can reason about causes and hidden relationships between variables that we define and also between data that we observe. This is called a generative model, which gives us a model of the world and some observations that we see. For example, say we observe that the grass is wet in this model example. We can then try to infer whether or not it was cloudy that day based on the data that we collect from whether the sprinkler was on and whether or not it rained. Using this kind of model, we can also try to automate how we infer this data, which is the main motivation of a probabilistic programming language. So probabilistic programming languages have had many applications throughout many years. Since the 1900s, Bayesian statistics and graphical models have been used in different fields such as physics, probability theory, and genetics. Currently, they're often used in fields like for medical diagnoses and also epidemiology, as is pertinent to the current COVID-19 climate. They're also used in speech recognition for natural language processing, as well as other fields such as causal inference, computer vision, and modeling structures. They can range from simple on the left to very complex on the right, which on the right, the example is a model that describes all the causes of liver disorder. So what does a probabilistic programming language do? A probabilistic programming language is an easy language for describing these generative models that allows us to quickly infer information about these models. As you see on the workflow on the right, there is a certain order in which we can use a probabilistic programming language to learn more about a model. So first, you choose your parameter, and then you define your model, which is all the causal relationships between these variables. After you get your observed data, then you can perform inference using an algorithm on the model to try and predict what the parameters that you want to know are. Some kind of inferences that we might want to make are, for example, to compare the probability of an observed outcome through different hypothetical models that we observe or we think we might observe. Another possible kind of inference that we want to make is to look for hidden variables in these models that we might not observe directly through the real world, but we want to try and learn more about through reasoning. So in our first toy example, we talk about linear regression, specifically Bayesian regression. Have you ever wondered how many C++ standards committee papers Bjarne Stroustrup is going to publish in the next year? we can try to model it using a linear regression example in our probabilistic programming language. So as you can see on the graph on the left, he looks pretty prolific. The trend looks kind of linear as we see, but there definitely is some noise in the trend that we're observing. We can try and model this noise in our model by introducing some Gaussian noise. Specifically, publications is a number of publications that we expect per year, and we want it to be drawn from a distribution, a normal distribution that is conditioned on different parameters. And we want to estimate the weight or the slope of the line and also the bias or the intercept of the line. So how can we try to do this in AutoPPL? As described in the workflow before, first we choose our parameters, in this case the weight and the bias or the slope and the intercept. Then we try to get our data, which is the year of the publication and also the number of publications for that year. Thirdly, we define our model, which is conditioned based on the weight, the bias, and we also want to find the publications. And lastly, we run our inference algorithm. In this case, MH stands for Metropolis Hastings. And then after running the inference algorithm to sample the posterior distribution of the model, then we can average these samples to try and get an approximate weight that the inference model thinks it is. So here are the results. The predicted W is 1.2 approximately, and the bias is negative 2,400. And this estimates that in 2021, Professor Strofstrup will publish about 12 standards committee papers, which is pretty on par with what we've seen so far.
So AutoPPL is able to achieve both high speed and a really elegant API using a number of modern C++ features. These include expression templates and operator overloading, and also C++20 concepts, which are a new and exciting feature in C++. First, users define data using, or define storage using PPL data and PPL parameter classes, which define places where people store their data and also parameters of the model. These have a number of methods and are totally generic. However, and notably, these are constrained by modern C++20 features. So they're extensible, but users are required to define classes and methods which have certain properties that can be extensible and incorporated seamlessly into our model. AutoPPL also provides a variety of distributions, which are, again, generic and use modern C++ concepts. Distributions provide probability densities, a PDF function, and a log PDF function. And they also allow users to sample from these distributions. So you can draw samples from or compute probabilities under normal distributions, uniform distributions, or Bernoulli distributions, among others. And notably, because AutoPPL supports a variety of key state-of-the-art sampling algorithms like NUTS, these distributions are fully differentiable. And we incorporate a complete autograd or automatic differentiation system into our language, which uses expression templates to efficiently compute derivatives and to sample more efficiently than a naive Monte Carlo sampler. Finally, and again, we have a variety of algorithms like Metropolis Hastings and a no U-turn sampler, NUTS, which are high performance Monte Carlo sampling algorithms. These are highly optimized and can perform sampling on a variety of generic distributions. As was noted before, NUTS is in fact a gradient or a Hamiltonian Monte Carlo sampler, which means that it uses gradient information computed from a highly optimized autograd system to guide the sampling process. And again, once a parameter has been defined and models have been defined, it's as seamless as calling PPL NUTS on the model in question to generate an arbitrary number of samples at high speeds.
So now that you have more background into how AutoPPL works, let's try a more complicated example, one of medical diagnosis. We can try and predict whether or not you ate expired food based on the symptoms that you're observing in relation to two common, I guess, diseases, cold or food poisoning. So let's say we observe these variables. We want to predict the probability of some of these variables, maybe the probability that you have a common cold or the probability that you ate expired food. We can try and make up some numbers for these probabilities. For example, let's say that the probability of you being food poisoned, given the fact that you ate expired food, is 0.8 or 80%. And also that the probability that you were food poisoned, given the fact that you didn't eat expired food, is 0.01 or only 1%. So here we can define our model in AutoPPL as the workflow before had mentioned. We have our parameters, which is expired food, common cold, or food poisoning. We have our data that we observe, whether or not you have a runny nose, a headache, or an upset stomach. And in our model, we can define all the different relations and the probabilities that we think we might observe, as we mentioned in the previous slide. So these numbers are actually directly from what we hypothesize the relations between each variable are. And lastly, we perform inference. So we observe that we don't have a runny nose, that we don't have a headache, but that we have an upset stomach. After observing this real-world data, we can then perform inference on the underlying parameters by sampling using one of our algorithms. From our algorithms, then we can average the samples that the algorithm provides to try and get the resulting probabilities. So the results are as follows. The probability that you were food poisoned is 1. The probability that you ate expired food is 0.89, and the probability that you got a cold is 0, which makes sense since we had an upset stomach but didn't have a runny nose or a headache. This also agrees with the true analytical results, which are pretty similar, as you see.
To test usability and performance, we built a sample model using one of the most commonly used libraries, which is cmd-stan-pi, a set of bindings for the stan library. We built the exact same model in AutoPPL and using stan's bindings, and then we used the same algorithm, no U-turn sampling. We also made sure to keep configuration consistent, the 1,000 iterations of warm-up and 1,000 iterations for sampling, and we tested on the same machine and conditions, including the same number of cores. The data we looked at was the life expectancy factor data from the World Health Organization, which includes alcohol consumption, HIV percentage, GDP, and life expectancy by country. So here's what this would look like in STAN. STAN has its own syntax for defining a model, and it gets inputted in its own separate file and then compiled by the compiler in STAN. Then later, the STAN defines the model by pulling in the file and then can call the sampling algorithm on it. AutoPPL looks a little bit different. First, we initialize storage for our parameters, and then we define our model. So we use the bar equal syntax to associate variables and distributions. So first, we define the different parameters for each country's data. And then finally, we define the data that we're trying to find. It's worth noting that we currently don't support matrix notation, which is why our model expression is not as compact as STAN's. But we're hoping that adding matrix notation will make this a lot more compact and easy to read in the future. Once we've defined the variables and defined our model, we specify a configuration for a sampling algorithm, and then we call a no U-turn sampler. So looking at the performance of each library, we notice that AutoPPL compiles twice as fast as STAN does. This might be because AutoPPL is a pure C++ library, whereas STAN has a built-in compiler that naturally takes longer to run. We also saw that the actual sampling was performed twice as fast by AutoPPL than with STAN. And again, this was tested with the exact same model, same machine and conditions, same number of cores, with also the same sampling algorithm and the same number of iterations each time. It's also worth noting that the AutoPPL actual numerical results are nearly identical to the ones found by STAN.
So now we're going to dive back into some of the technical details of AutoPPL. so that we can highlight some of the ways that modern C++ actually makes it possible to have a modern, highly optimized probabilistic programming language without its own custom compiler. We're going to talk about variable expressions and distribution expressions, which are made possible using operator overloading and expression templates. Model expressions, which are again supported by concepts and expression templates, and a variety of sampling algorithms, which include a custom autograd system, which is again, in fact, made possible by modern expression template usage. Returning to the AutoPPL core workflow, we describe how first a user can define data using PPL param and data classes, define an efficient model, which is an elegant wrapper around that data, and then call a variety of generic sampling algorithms. Crucially, this is made possible using a variety of variable and distribution expressions. And essentially what these are operator overloading generated abstract syntax trees, which are compiled and generated at compile time and allocated on the stack. This means that instead of having to do a classic heap allocated graph to describe the abstract syntax tree, all of this can be generated at compile time and ordered contiguously on the stack. Distribution expressions are the same. You can use arithmetic expressions to combine normal distributions or combine random variables to generate highly optimized, highly efficient, and very complex random variables. Model expressions are very similar, and they're at the core of our language. These also use operator overloading, in this case, the bar equals expression. And it means that these models can be generated at compile time and allocated on the stack. These models can be extremely small in terms of memory overhead, even when they look extremely complicated. So for example, a model that is 10 layers large and has a variety of non-trivial dependencies is typically less than 500 bytes on the stack. And it merely acts as a viewer over existing data rather than owning its data, which means that users can define where their data should be stored, and the model simply refers to that external data. Notably, this means that all of our memory is allocated contiguously, so that sampling algorithms that require high efficiency and cache coherence perform extremely well and competitively with a hand-engineered implementation.
So why do we need concepts? We first list out some of the things that concepts help to solve. So for instance, the compiler sometimes chooses the wrong function template overload. And a lot of times concepts simplifies code. It removes these loopholes where metaprogramming type safety can be bypassed. And in general, it just generates more readable code. But in expression templates especially, type constraints are needed. And it's because that it's similar to how we define a grammar in a language. All of that rule is actually stored within the types. And so as an example, when we write something like variable bar equals some distribution expression, which can depend on other variable expressions, we want to forbid users from having a similar kind of expression to not compile if any one of those three things do not fit a certain constraint. So this is similar in the spirit of how a compiler generates syntax errors. So we ran into a problem when we were developing this library, and we did in fact see the compiler choose the wrong overload. So consider an unconstrained template overload of operator minus defined below. So we see here, it just takes in two generic types, left-hand side type and right-hand side type. We use forward universal references and forward them to the helper function. But note that they are not constrained in any way. This is completely unconstrained, and they can be any types currently. And we also note that other libraries, such as stdchrono, overload these operators. So within our library, another use case of stdchrono is a function like update time. So in this function, we first take the time of the current stage, and then we call a routine to time, and then we take the time again, so that we can check the duration and maybe update some variables accordingly. When we compute the duration, we see that we have to write this expression end minus begin, which uses the operator minus. And the error is that the compiler keeps choosing R overload. And we see this in below where we highlighted red and bold, that it is indeed choosing PPL : operator minus and not the chrono operator minus. So using pre-C++20 metaprogramming tools, it is possible to solve this issue. Here's one solution, and the code in red is the extra portion that we included to solve this issue. Specifically, we use enable if, and we defined these context for booleans, such as is not both arithmetic underscore v and is valid opparam underscore v, to check if the types meet certain criterion, and if so, this substitution is allowed. So in order to do anything like type constraints pre-C++20, you have to use SFINE, which stands for substitution failure is not an error. And this specifically refers to the usage of enable if. To take advantage of the auto keyword, we put this SFINE technique as a dummy template parameter. It's more common to see this enable if used as the return type itself for function templates. But because you cannot use auto as the second template parameter to enable if, and we really, really wanted to use this because operator minus is just a delegator, it simply delegates to this helper function, so it should return whatever the type the helper function returns. We had to resort to this technique of making a dummy template parameter. But this introduces another problem in that a user could simply call this operator minus by feeding in the template parameters themselves. And in particular, defining a template parameter as the third one. So for this operator minus using C++20 concepts, it looks a lot simpler. So at the beginning, you can simply say that the left-hand side type and the right-hand side type follow these concepts of valid opparam. And you additionally require that they are not both arithmetic. So we see here that there's no use of this dummy template parameter. We still get to use this auto keyword. We have the same constraints, if not more, because concepts are a lot more versatile than the pre-C++20 metaprogramming tools. And most importantly, the code is more readable. And for completion, we show the concepts for valid opparam and not both arithmetic. So we define valid opparam as either an arithmetic, or it's a variable expression, or it's a variable. And var expr and var are two concepts that we also defined in a separate file. The motivation for these definitions is that we wanted to compile expressions such as the following: x minus y plus z, the whole thing minus 3 minus 4. So just to be extra safe, we wanted to avoid overloading for two types when they are both arithmetic, because that is illegal by C++ standard. And in general, when we work with operator minus, you will have on the left-hand side or the right-hand side variable expressions such as y plus z, or it could simply be a variable such as x. So the supported features are, we have ways to define data and param. We have a way to construct models using distributions such as uniform, normal or Gaussian, Bernoulli, and discrete. And we have inference algorithms such as Metropolis Hastings and no U-turn sampler that work on these models. So in terms of testing and benchmark, as well as continuous integration, we use Google Test. Currently, we have about 110 unit tests. We used Benchmark to perform the benchmarking against Stan and PyMC3 for other examples. Continuous integration, we use Travis. Currently, we are supporting Ubuntu 14 and the 4 compilers by G++. And we also check for test coverage using coveralls. And here we list the third-party tools that were used for this library. So Armadillo is a matrix library, Clang, CMake for build system and compiler, coveralls and CPP coveralls to check test coverage. FastAD, the automatic differentiation library, which is a big dependency for our project. GCC, again, is just a compiler, benchmark and test. CI was explained before, and Valgrind for testing for memory leaks. So in the future, we hope to support more distributions. And as noted before, we would like to support matrix notation for simplifying model expressions. And we would like to also improve and extend FastAD to implement more optimization-based algorithms, such as map estimation or other Hamiltonian Monte Carlo algorithms like NUTS. And lastly, we would like to support more variable expressions, such as sine of x or cosine of x and so forth.
Finally, we're going to give what is in fact not at this moment a live demo, but an example which shows, in fact, some of the code that was used approximately for benchmarking our library. So this is an example of code that you might find which uses our library. In this case, we're going to load data in from a CSV file, data which includes information about how life expectancy correlates with alcohol usage, HIV and AIDS prevalence, and the GDP of a source country. After we load the data in from a CSV, we can define a variety of variables and parameters, and we can allocate storage for them. Then we can use our syntax to define a model. And this is simply a stack allocated wrapper around the data we've allocated, which describes priors for our data, and also a linear model which we assume correlates alcohol, HIV and AIDS, and GDP with life expectancy. So this is similar to the example we gave earlier with Bjarnian regression, but where we use a linear model with Gaussian noise to try and find a correlation. Finally, we can use a sampler like Metropolis Hastings to draw samples from the posterior distribution of our model. But note that we could have just as easily used a more sophisticated example like NUTS, the no U-term sampler, which is just another algorithm that can be dropped in to perform the same kind of sampling. Finally, once this is called, we can use a simple sample average, an accumulation-based averaging function to compute a mean estimate for the parameters that our sampler has predicted. So here we can interrupt PyMC3 and try and build and compile our own code. So here we'll jump into the release directory and run make. And you can see it's compiling using a standard Clang compiler. And there we go. It's compiled, including our tests, which are already built. Now we can run it. And you'll see that, okay, we draw a certain number of samples. And now here we go. Here we have estimates for the mean of our different coefficients and for the bias. So in this case, you can see there's a 62-year offset on the life expectancy, which makes sense because 62 is probably the mean life expectancy on our data set. And you can see correlations with different features. So for instance, HIV and AIDS has a strong negative correlation with life expectancy. GDP has a slight positive but fairly small correlation. And alcohol actually has a strong positive correlation, which I can only assume is some quirk in the data set. Maybe alcohol usage is a sign of wealth, so there are hidden dependencies. But it's notable that because we can build these kind of generic probabilistic models, we could try exploring that. We could try building a model that has a causal relationship between GDP and alcohol and see to what extent that compensates for some of these surprising outcomes. And it will just note that this agrees with a variety of other libraries like STAN and PyMC3. So thank you for listening. I hope you found this useful. And as always, stay safe and be well.